Hey guys, would you like to know if the Kohinoor diamond will disintegrate someday? Why? Because you know very well that carbon plus oxygen gives you CO2. There's plenty of oxygen in the atmosphere, and well, diamond is nothing but an allotrope of carbon. And if it does, when? How long will the Queen Elizabeth get to wear it? Let's try to understand these questions. So, integrated rate equation. In the last series lecture, we talked about the rate laws, where the rate of a reaction, which could be described as the reduction in the concentration of a reactant over time, is proportional to, and I should say not proportional right now, is equals to a constant multiplied the reactants. Let's say A reacts to form B, the concentration of the initial concentration of the reactant. And then you can have a power above this and you start calling that as the order of the reaction. I hope you remember that. So the rate law basically relates the rate with the initial concentration of the reactant. What the integrated rate equation does is basically it relates the concentration of the reactant with time. So this is what we'll be trying to understand today. Now, integrated rate equation, we'll be doing that for zero order, first order and second order reaction. Now let's first keep it simple and try to do for the zero order reaction. Now starting, we very well know rate equals minus d concentration of A upon dt equals K, that's rate constant, and that multiplied by A to the power 0, zero order, right? Now let's try, so this eventually goes out to be 1. So that means minus d upon A equals K dt. Now I'm going to miss a very crucial detail here. So this reaction is about A goes to B. What about AA goes to BB? A is the stoichiometric coefficient, right? I hope you remember that from the last video on the series. So that means we must have added 1 upon A here, and this will jump over to the right side. So AK dt. Now, very simple, let's integrate both sides. For the limits, what should be the limits? Let's try to understand that. So, at time t equals 0, the concentration of A equals A0 or A0. The reaction proceeds to time t equals t, and the concentration of A at that point becomes AT, right? So we have to integrate the amount of reactant that would be formed at that time. So the limits can be A0 to AT. Remember, I have excluded or brought the minus sign outside because it makes no difference. The rules of integration and differentiation. And so here we have to say t equals 0 to t. Okay. Now, the integration results in something that is going to look like A, and to apply the limits, so the result of the integration is simply A, and you have to run through AT to A0, and AK, they are constants, right? So constants don't integrate, they just simply come out, and that will run from 0 to t, right? Now, so that means, okay, and don't forget the negative sign there, right? That means AT minus A0, let's not forget the negative sign, equals AKT, because t minus 0 is t, okay? So that means if you rearrange, you can come by A equals A0 minus AKT. This is the integrated rate law for integrated rate equation for a zero order reaction, and it is relating the concentration at time t with the time and the initial concentration. Now, I want you to be able to derive the same for a first order reaction. What I'm going to do is take a pause and allow you to work on your own, and then we'll resume. I hope you have worked it out, and I'm going to be a little fast because I assume you must have worked it out, right? So this is already the rate law. This is what rate law gives us. So let's try to bring all the a towards one side, right? So that gives us minus d a upon a equals a k dt. Now we already know what happened with ak dt, that is akt. So I'm not going to do that again, right? Let's simply write it down as a final result because that is the fate, akt. Let's just worry about this one. So when you integrate this, what do you get? You get, using the logarithm obviously, so 1 upon a concentration of a, that transmits to ln, that means logarithm. So ln a naught minus ln a equals akt. Now remember, there's no negative sign here. That means I have already used that. Okay, so this is the rate equation for the first order. If you try to find the same for a third order reaction, that would also be very simple, and it would come out to be 1 upon a minus 1 upon a naught equals akt. Now the pattern that you must understand right now at this stage is this guy is going to remain fairly constant, right? It doesn't change. What changes is the other side. Okay, so you have to just apply the rules of log and you have to come about this result. Now something is very interesting here, something that scientists refer to as the concept of half time. That means at the time at which a naught goes to a naught by 2, aka at becomes a naught upon 2. Now if you do the same with these equations, you can calculate half time for these. So let's just say a naught upon 2, because at is a naught upon 2 for half time, right, equals a naught. Now you can use the brackets, you should be using the brackets, minus akt. Now we want t, because this t is very special t, it's t half, it's a half time, right? Now if you rearrange that, it comes to be about t half equals a naught, there's no at here, a naught upon 2 ak. You can calculate the same t half for a first order reaction. That will come out to be around ln 2 upon ak. This is all just calculations. Since this is not a mathematics lecture, that's why I'm not overdoing those stuff. But yeah, this is all mathematics. And if you try for this little guy, that is a second order reaction, that will come out to be about 1 upon ak a naught. Now how are we going to use this to solve problems? Because that is what we want to, right? Now let us see what practical use of this knowledge we have. So here's a question. A certain insecticide dissociates according to the first order kinetics. How do we know it's first order? I hope you remember the rate law. We derive it via experimental observation. It will not occur or be calculated, you will have to derive it. Okay, so with the rate constant, so this is the value of k, that's per year. If a decent sewage dump raise the insecticide concentration to 5.0 into 10 to the power minus 7, that is your a naught. How much of pesticide will be left after an year, right? So in year, that is the t. So first order kinetic equation, I hope you remember the formula is ln a naught upon a, remember this is inside this, at, not at, equals akt. So here, what do you already have? you have K, you have A naught, you have to find what is AT, and you also have T. Now A, first order kinetics. Now although stoichiometry is not always equal to the order, but here in this case we can assume that this is, because it's not explicitly mentioned, so we can simply assume that that is the case. Okay, so let's do that. Now you can do the calculation of this factor, and this will come around to be 1.2 into 10 to the power minus 7 gram per centimeter cube. Now it's a very important thing that frequently confuses people, is to check the unit of the rate constant and the time. Now both of them were in years, that is why we did not take the pain of converting anything into anything, right? Now this was pretty simple, right? Now often you might have heard in the news, some lake, some river, some water body is not fit for a human visit. So bring that into perspective and give you a real insight into how these things are important and how do they actually matter. So the safety limit is 3.0 into 10 to the power minus 7. By what time will the government allow people in the lake? So you have everything here. I hope you can recognize it's the same problem. You have A naught, you have A T, you have K. What you have to determine is T, by what time. So I will leave this as a homework and the answer would be dropped down in the comment. Before I leave, there's one final thing that I want you to understand by seeing this equation, right? So sometimes you'll have the concentration and concentration of A measured at various times, right? And you might have to determine the order of the reaction. Okay, so zero order, first order, second order. Now if you see these equations, something will appear to you. They are all of the form y equals mx plus c. So y equals mx, t is x, plus c. Y equals mx plus c. Y equals mx plus c. So if you have the data and if you can convert it into these exact stuff, so if you plot a graph between AT and T, so y mx, right? If you plot a graph between AT and T, and if your graph is a straight line, that's a zero order reaction. But if the graph is a straight line between ln AT and T, then that will be a first order reaction. You should be mindful, minus, right? So the graph will look something like this. Again, same 1 upon A and 1 upon NT. So if you plot here 1 upon A and T here, it should again be a straight line. So this is how you actually try to find out the order of the reaction by using experimental data. Now this is a practice question for you as a homework. The table gives concentration of NO2 against time at 300 degrees. So you already have been given the various concentrations for NO2. Okay. Now what you have to do is you have to find out all the possible values that you want to investigate. Now what is the reaction? Very important. NO2 gives NO plus half O2. This is a balanced stoichiometric reaction. Okay, so you have to find, is it first or second order? So what should your steps be? I think you already have a fair idea, and I'll look in the comment section for your answers. I hope this helps you. Thank you so much.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.